this talk is really aimed at looking at how we combine PET-MR together in the context of reconstructing the images. So here then I'll quickly review the super basics of the core of PET reconstruction and show you the problem of noise that is the main issue with PET reconstruction, and then rapidly talk about MR reconstruction basics, again identifying the problem as being undersampling due to trying to run things faster and faster in terms of acquisition, and also noise can be an issue. But then the real focus of this talk is going to be this series of methods here. Okay, so how we introduce MR mainly into PET reconstruction, because it does tend to be a one-way street, really, if I'm being really honest with you. There are some benefits that MR can get from PET, but mainly it's PET benefiting from MR. So I'll talk you through the so-called Kernel method, and then guided regularization methods, making use of MR information, as well as self-guided PET, and then synergistic reconstruction, where we combine the reconstruction of the MR with the reconstruction of the PET simultaneously into the objective function of the reconstruction. Then I'll touch on my favorite topic, AI, deep learning, and also mention some of the current research I'm supervising with one of my students who I think is present in the call here, so he'll be able to answer any questions on that. But again, at the bottom, notice here the reality is that it's largely PET reconstruction that is benefiting from MR. But that said, notice in italics here, these methods that I'm presenting to you where we're using MR to help PET, notice you can use MR to help MR. So in other words, if you have a great quality T1 weighted image, you could treat ASL, so to speak, as if it's something like the PET, not as high quality, and you could use your T1 weighted MR to assist your ASL reconstruction. In fact, I've done work on that with a former postdoc of mine. I'm not covering it in this talk because this is about PET-MR, but just to say these principles are quite general. Okay, so super basics of PET image reconstruction. We've got a radio tracer distribution inside the brain here, inside the field of view of a PET-MR scanner. I'm just showing some PET crystals here. And this is a radioactive concentration F as a function of X, Y, Z, and time. We've got this inside the PET-MR scanner, and we're collecting typically about 800 to 1,000 sinograms. And I refer you to my talk from yesterday to go into the details of how we get those sinograms. And I'll take it as read that you understand, although I will be reviewing it very quickly, how we iteratively obtain an image from the PET sinograms from the PET-MR scanner. So that's the PET pipeline. I'm going to be focusing obviously on the reconstruction aspect here, because then simultaneously we've got some kind of net transverse magnetization. I'll refer you to all the MR talks from yesterday inside the brain here, inside the field of view of the PET-MR scanner. And so we've got case space that we're collecting, and then we could, if we have fully sampled case space, we could do some kind of inverse Fourier transform or least squares method, compressed sensing, you name it, whatever your favorite MR reconstruction method is. And so what I'll be doing now is just talking you through just graphically the super basics as a refresher of how we get these images, and then I'll talk about how we combine them to improve reconstruction. So in PET, most of the methodology, and I've just confirmed that today, as you heard my questions earlier. So if we're talking about the MMR scanner, the reconstruction algorithm is really as simple as this, okay? And so to explain it, we're considering we've got some ground truth distribution inside the scanner, and we've got maybe 1,000 such sinograms that have been collected from the PET data. Here I've not got any noise. This is just a simulation here, but I'll be mentioning noise definitely in the coming slides. But just to talk you through the process, what we have then is some initial reconstruction. It's uniform normally. We just assume nothing at all about the image. And that's this theta here as just denoting a uniform image. And then what we do is just simulate what the PET scanner would have done. That's what this matrix A does. And I refer you to the talk from yesterday where I talk about in detail how we model positron range, how we model the geometry, attenuation, normalization, random, scatter. Basically, we can put it all into this forward model to just predict what our scanner would have done had that been in the field of view. And then we compare it to the measured data, the measured sinogram data. We just simply take a ratio. It's an unbelievably straightforward process. So basically you have an image estimate, predict what the data would have been, compare it to the measured data in this ratio, And then we do a back projection. We do the transpose or the adjoint of that forward model of what the scanner is doing. And that's typically known as back projection, to then use that to multiply our current image. And if we keep going like that, you can see that this image will progressively get closer and closer and closer to what the ground truth was. Now here, notably, this is a simulation with no noise, and you can see that this image is getting closer and closer to the ground truth image just by a simple forward projection, ratio, back project, multiply. That's at the core of all that we're doing in PET image reconstruction. Now, MR is very similar. I won't go into it in detail, but basically it's a very similar process. Here you would have your T1 weighted MR image. Your forward model would be your Fourier encoding matrix. So in other words, with parallel imaging, that's going to be your coil sensitivity maps, discrete Fourier transform, then your undersampling operator to strip out the K-space values that you don't have. So you just have an overall system model there that you're applying to predict the K-space data. And then instead of doing a ratio, because with MR it's a least squares problem, Gaussian noise model, you just do a subtraction, you just do a difference. And then the back projection here is again just, in fact, just the transpose of that Fourier encoding operator. So in fact, for the fully sampled data, that's just an inverse Fourier transform when you solve it in one go. But just to say that even with MR, it's as simple as what I just showed you for PET there. It's just an iterative process of forward modeling, looking at the difference, backward modeling, and using that to modify your reconstructed image to get to a better result. So that's the core methodology to PET and to MR reconstruction. But the focus of this talk, as I've said, is now going to be how we seek to improve these reconstructions. But why is it that we even need to improve these reconstructions? Well, for PET, really, it's the problem of noise. I've just shown you some highly idealized noise-free data there. But in reality, we have limited scan time, or indeed we're reducing scan time, or we're reducing the injected dose. And for that reason, we don't have such high quality data. We have quite noisy data. So you can see here, I've taken that noise-free data set and introduced increasing levels of noise, which corresponds to reduced injected activity or reduced scan time. And you can see that our beautiful reconstructed image rapidly downgrades with loss of counts, of course, in PET. So that is a problem, and we seek to resolve that by a process known as regularization. I've put a copy of a photo of a jumbo jet here because that's behind this idea of reducing dose to maybe the 0.1 millisievert level. So maybe a factor of 100 reduction would get your PET dose to be something like a intercontinental flight, which would be quite appealing. But anyway, we need to regularize to compensate for that noise problem. Okay, with MR, with fully sampled data, all is well, but again, we want to reduce the scan time. And so I've just given one example here of reducing the sampling. If we don't do anything about it, then we get the well-known aliasing artifacts in the reconstruction. And so again, we need regularization or compressed sensing methods, which I'm sure were covered yesterday. Okay, so that was a rapid review of PET reconstruction, MR reconstruction, and the need for regularization. Now let's look at this batch of methodologies I've listed on the screen here to see how we can go about helping the PET reconstruction with the MR data. So the first method is going to be the Kernel method. This is extremely easy to understand. Basically, it's the method that was originally proposed by Wang and Chi back in 2015 in the context of just PET only, but here it's been adapted to MR. And the essence of it is as follows. So imagine we've got some MR data and some PET data here. This is binding potential maps for sharing compound carbon-11 labeled radio tracer. And you can see that normally in PET reconstruction, the images, which you can see here are very noisy, are made up of pixels or voxels. And so I've represented those pixels or voxels as just a white dot in the middle of this patch. So imagine that white dot as being any one of the pixels in that image. And it's because we're using such small pixels that we end up with quite significant noise. So what we can do with the Kernel method is take an MR image, consider every region, every patch of the MR image, zoom in, and we can compare the pixel values within a patch of the MR image. And if we do that, we can get a similarity map. So all we're doing is saying how similar is that T1 weighted grayscale pixel value to that one, to that one, to that one, and we end up with this similarity map. And we can use that similarity map instead of pixels or voxels within the PET reconstruction. So we're no longer finding what are the amplitudes of pixels or voxels for PET reconstruction. Instead, we take clusters of voxels or pixels based on similarity maps from the MR. It is that simple. And we use those distributed building blocks in order to create the image. If we do that, you can see, so there's an example of just one of the building blocks used in that corner of the image. And you can see we get significant noise reduction just by copying MR similarity anatomy and using that as the building block in the PET reconstruction. So this is a very powerful method. There it is in the equation form, but all we do is just simply put in a matrix B. But let me focus on the results rather than the mathematics. And this will show what happens, for example, if we go from 100% dose PET reconstruction down to, say, 1%. If we use pixels, then we get that well-known problem. If we use those kernel basis functions, those MR similarity maps, those clusters of pixels based on similarity, you can see that we can tolerate much lower levels of counts in the PET data. And this is work I published, supervised by student James Bland. In fact, Alexander was also involved on the paper. Okay, so that's the rather successful kernel EM method, which is good, but it's still maximum likelihood. Purists out there would want to properly change the objective function in the reconstructions. That's what I'm going to do in the next approach. And it's very similar to the stuff that you've just seen for the kernel method, but it's just now getting a bit more sophisticated by building this into the statistical methodology. So the methods I've just been showing you for PET are maximum likelihood. And if they use pixels, we've seen they can be noisy. What we can do is build in a probability of particular images. And this is known as maximum a posteriori instead of maximum likelihood reconstruction, where what we're saying is that the probability of an image is related to what we're going to define as an energy of an image. And what we're saying is we want images with low energy. So noisy images have high energy, good images that we say are good have low energy. And that's going to be encapsulated in this probability, this audacity of saying we know what the probability is of a given image. And I'm just going to show you now how we define the so-called energy for a PET image. So here's a typical PET image, and just going to zoom in on that. And then what we're going to do is look at pixel values within some patch of that PET image. And the energy is just saying, what is the difference in those pixel values? Okay, so in other words, if there's a big difference, that's high energy, that's bad. And so what we're going to do here is assume that we want low energy images. We want pixel values to be comparable, similar. That corresponds to low energy images that we consider to be more likely. Now, obviously, we don't want positive and negatives to cancel each other out here. So we need to either take the I'm using psi here to denote some function. Typically, we look at the square difference. It could be the absolute value. You may have heard of TV or total variation. Well, all you do for total variation is just take the absolute value of those differences and then look all over all the patches in the image over all the different pairings. So there are many options. But here in this work, I'll focus on the case of a quadratic difference. But also you might want to say, well, actually, these pixels, we'll allow them to be the same value if they're a long way apart. We can deal with that because, in fact, there could be legitimate edges. Of course, you know, here we're in the white matter, here we're in some gray matter here, and we do want to allow some differences there. So this is just a way of measuring how noisy an image is. And so all we do is just look at these differences over all the pairings in some patch, and then add this up for all the possible patches in the image. And that's going to give us an overall energy measure, which allows us to say how probable or not an image is. So that's conventional map reconstruction, which we've touched on earlier with the industrial talks. And we know that one manufacturer does do map methods and another one has not yet really been doing that. But how do we get the MR information in there? Well, okay. What we can now say is let's put in a little kind of a weighting factor in here that can kind of switch on or switch off or modulate how important those pixel differences are. So remember those similarity maps from the kernel method I've just shown you. Instead of using those similarity maps as building blocks for the reconstruction, we can use those similarity maps to guide the level of energy measurement in these priors. Okay, so again, we've got a nice patch here from an MR image. We can generate a similarity map of the grayscale values in a T1 weighted image and use that to say, well, yep, I want to apply this energy function. In other words, we want pixel values to be the same. We will allow that to be the case across regions in the MR that are comparable. But in this direction, what we're going to say is we'll actually switch off this penalty, this energy measure, and say, well, actually, if there's a big discrepancy, say across, then that's actually okay because that difference is present in the MR image. And so we can modulate the impact of this energy term. And so that allows the MR to have an influence on the probability of a given image for PET. You may have heard of the Bauscher method. Well, the Bauscher method is doing exactly what I've just described there, except it uses this binary set of weighting factors. Now it says, yes, we're going to insist on low energy across this region here because it's similar in the MR, but there we're seeing a difference in the MR image, and so therefore we're going to switch off that energy penalty across that MR boundary. Okay, so let's take a look at how we would do that. I don't want you to be afraid of that formula there. So all you need to see from this slide is what I put in words here and say that we just do an iterative update of our image just by taking the conventional reconstructed image that you saw me give you graphically earlier, that simple forward project, ratio, back project, multiply. And then all you do is to get the update is you keep that simple method and then you divide it by a combination of that simple update with what turns out to be just a guided smoothing of your current PET reconstructed image. In other words, you use that, for example, that Bauscher similarity map to control smoothing within regions that are similar in the MR, and you switch off the smoothing in regions that are dissimilar in the MR. So it's actually a very simple approach. These are the kind of results that we would get from that. Imagine we just use regular MLEM with a post-smooth for only 5 minutes of fluorbedaben, fluorine 18 labeled fluorbedaben data here. If I use the method I've just talked you through, the Bauscher prior, then these are the kind of results that we get. Now here, what I've done is allow a large neighborhood, which is effectively saying, you know, we don't care about MR similarities, let's just include it all in that energy term. And so it effectively does smoothing even across boundaries. But as we reduce the number of similar neighbors, if you like, in that similarity patch, then we start to only smooth selectively within regions that are similar in the MR. So it's purely PET data that's being used, but we're using the MR to decide whether or not we aggregate PET data in particular directions. And so that's why if we only have 15, that's a smaller, more compact neighborhood that will follow MR anatomy. Okay, so there are catches with this kind of approach. Now, what if you've got a unique PET feature and it ends up and it's not in the MR? Then obviously that can get blurred out because the MR is giving permission to smooth. Well, that's where we've come up with more sophisticated methods that not only use the MR to guide the reconstruction, but also use the PET to guide the reconstruction. And so this is what a former postdoc of mine, Abafaz Moranian, called anato-functional PET reconstruction. And it includes the current PET reconstruction. So imagine this is the current PET image, just a section of it, and this is a section of the MR image. What we can do is look at the similarity maps in the PET, similarity maps in the MR, and then we can take the product of those similarity maps and build that in as a guiding factor for that regularization. If we do that, then the long story short is that we get improved image quality. And I'll show you when I get to the next set of slides in a moment for synergistic reconstruction, how that kind of approach can help preserve PET unique features that otherwise might be blurred out with a naive Bauscher or MR guided regularization. Okay, so let's move on then to synergistic reconstruction. So here, the plan now is that we're still going to use, I'm afraid I have to refer you to the talk from yesterday where I talked about the PET Poisson log likelihood. Basically, it's just a measure of agreement between your reconstructed image and your Poisson distributed noisy sinogram data. So we keep the PET data fidelity, and then we have the MR data fidelity, better known as least squares. If you take the logarithm of a Gaussian, you've just got a least squares, a weighted least squares objective function. So that's all standard in synergistic reconstruction. And the whole secret is in how we define that energy term, which I've been calling U up to now. And here I'm using R because this is based on the work of my postdoc. And I'm just saying that I'm using all the conventional stuff that I've talked about before. I used matrix A before for modeling the entirety of the PET acquisition. And I'm still using a Fourier encoding matrix E, which is including the Cole sensitivity maps and the discrete Fourier transform and the undersampling, in other words, the case-based trajectory. So that's all built into the data fidelity. The focus here for synergistic reconstruction is not the data fidelity, but rather the prior that accommodates both the PET and MR in a combined way. So it's very similar to what I've just shown you. So don't get too intimidated by those expressions. In fact, you should recognize them already as being very much the same as what I've been talking about. So we look at the PET image, we get a similarity kernel. We look at the MR image, we get a similarity kernel. All we do is take the product of the current. Now notice here the difference to what I've been doing before is that here we're iteratively updating our MR as well as iteratively updating our PET. And as we go along, we calculate for the current iteration, what is the similarity map at each and every pixel location. Okay, and then we take the product of the similarity maps. The reason for doing that is that it allows you to preserve unique information in the PET, unique information in the MR. And in fact, you can do this for multiple MR contrasts, your T1, T2, flare, whatever it might be that you want to include in this synergistic reconstruction. So you take these in a product, and then you just use those as the guidance weights for the for this joint penalty. In other words, we've got an energy penalty for the PET, energy penalty for the MR, and in fact we do it for all of the MR images, however many contrasts you're dealing with. So it's a very simple method. Okay, if you want to review this, go back to what I said about the kernel method. If you understand that well, this is just doing that same kind of kernel calculation, but for multiple MR contrasts and the PET, taking it in product and putting it into a guided regularized objective function. Okay, the mechanics of how we do that, it'll be just what I've talked you through before with the MAP-EM method. That's exactly what I was talking about before. But now we have weights that come from the current MR as well as the current PET reconstruction. So the weights are dynamically adjusted as you iterate. For MR reconstruction, we're just using the conjugate gradient, penalized weighted least squares. So that's effectively a regularized version of that brief MR formula that I gave you earlier. But the key that you need to take away here is it's the weights. Okay, it's just the product of those similarity maps that I've been talking about. If we do that, this is a key bit to understand, is that if we look here, so just to say this is the MR that's being reconstructed, this is the ground truth PET that's being reconstructed, that's the noisy MLEM in the top right corner there. This will be a conventional, this is just total variation denoised MAP-EM for PET. Now, if we did conventional MR guidance only, so obviously you take a fully reconstructed MR image and you use that to regularize, to guide the regularization for your PET, what you're going to see is this problem here, where notice this feature in the PET is absent from the MR, and so that means the MR information is going to incorrectly guide the smoothing of the PET data, and we end up with this very misleading feature. Whereas if we do the synergistic method that I've just been talking about, where you allow the PET to also develop the guidance information, also as the MR is developing the guidance information, then you can nicely get this kind of result here, where that PET unique feature is retained without misleading MR guidance information. So this was work published by my former postdoc, Abfaz Moranian, in Magnetic Resonance Medicine 2019. Mutually weighted quadratic priors is the name of the work. For real data from the MMR, these are the kind of results that we see. Maybe I should focus first of all on the fully sampled case. That's what we could only ever dream of getting. But obviously what we're dealing with is undersampled MR data. Here's the total variation regularized reconstruction. This is the weighted quadratic. That's the guided quadratics. That's using, I think, a fully sampled guidance image. Now, with the synergistic method I've just been talking about, long story short is that it does outperform these other methods in terms of reconstructing undersampled data. So this one here is closest to the fully sampled data. This is for T1 and for FLAIR sequence reconstructions. And then putting the PET in there as well. Again, maybe I should just focus on the undersampled MR. We've got the familiar aliasing artifacts here that are visible in the FLAIR and in the T1. We've got the noisy MLEM. If we do a conventional regularization, total variation for sense reconstruction for MR, we get this result. Total variation regularization for the PET, we get that. With the synergistic, well, we've got that mutually progressive building up of the guided regularization as we reconstruct the MR, as we reconstruct the PET, then again, we do seem to obtain improved image quality. And for the MR, of course, we've always got the benefit of the reference being the fully sampled. I just wish we had a reference, of course, for the PET. Typically, that's going to be the high count data. Okay, I've got about 10 minutes or so to cover deep learning based methods now for PET-MR reconstruction. First of all, this is just reiterating what you saw from an earlier presentation where, and I talked about it in my question actually, where what you can do, this is work from Georg Schramm, published in Euroimage 2021, what you can do is take a conventional OSCM image. I've shown you the methodology here already, how simple it is to obtain that. You can take that with a fully reconstructed T1 weighted MR image, put those two as an input to a convolutional neural network. Here it's a residual convolutional neural network, which means we're just trying to learn what is the difference between what we want and what we have. And what we want here is an MR-guided, a Bauscher-guided PET reconstruction, which normally takes much longer to reconstruct compared to an OSCM image. So all they did was train up a network to learn how to map a conventional OSCM and a conventional T1 to the higher quality regularized computationally intensive reconstruction. So this can be viewed as an accelerated way of obtaining MR guided reconstruction. But the benefit was they also included higher count data in their MR guided reconstruction. So that's a beautiful concept whereby you can have a lower count OSCM reconstruction. You've got your T1 weighted image, and then you learn how to effectively upgrade the statistics based on the MR information as well to get a higher quality PET reconstruction. But the main goal of their work was really to reduce reconstruction time. So with the CNN, they were talking anywhere from a minute down to a second compared to maybe an hour plus for a CPU-based reconstruction. And they just used mean square error loss for their training of the CNN. And this is just a very conventional vanilla CNN, nothing exciting, not even as complicated as a UNet. So very, very basic indeed. Okay, but what I focus on is more elegant solutions whereby we embed deep networks inside the image reconstruction process. So in the closing minutes, I'll touch on how we do that. So at the top of the screen there, I've got the vanilla OSCM MLEM reconstruction just represented as a cascade of operations. Okay, that's how you need to be thinking about deep learning AI. Always dealing with is like a program. It's just a sequence of steps, sequence of layers. You go from input to output. So our conventional MLEM reconstruction is an initial image going through a series of steps. That should be familiar. That's a deep network. Okay. Here, though, we have no trainable parameters in our conventional EM reconstruction. All we have is the sinogram data going into our conventional EM update formula, and we get an output image. Now we know if the sinogram data are noisy, then we get a noisy last iteration. And we also know from the MapEM methods I've talked about that we can try and curtail noise by doing a denoising step. So that's that guided, MR guided smoothing process. And in essence, the regularization is just taking the current estimate, doing a guided smooth, combining it or fusing it with a regular EM update to get the next iteration. So what I'm showing here is conventional reconstruction and then map EM reconstruction, just as a cascade, as a sequence of operations. Because once we put it in this so-called unrolled format, whereby it's explicitly already like a deep network, all we then need to do is say, well, actually, we don't really know how to best denoise. We don't really know how best to use that MR information. I know, let's learn how to best use the MR information based on training data. And that's what deep learning is all about. So as mentioned here, the methodology here is mathematically convenient, unlikely to be optimal. Deep learning will use the data to tell us how to best use that MR information. So this is what we do then. This is the key concept. Notice that we use a high quality reference. That's another very key component to AI, deep learning, is that you've got to have your high quality reference or label. So here with simulated data, we have a very high count data set with improved resolution, whatever it might be, and we've got a very high quality endpoint iteration. Okay, that's our target for our training. And then what we're dealing with is noisy data, very much in a cascade of operations that you've just seen for the previous map-EM. But now what we're doing is taking the current image, learning how to denoise it, such that a denoised version of that can be used as a guiding prior for the database update, which is just then fused together to give the next update. So it's a really simple process. All we do is take an initial image, run it through, and initially this network is just randomly initialized. This could be doing all kinds of nonsense. It's going to be producing some maybe useless prior, combining it with the EM update to get a next image, and it's going to give us a suboptimal result when we initialize. But what we do is we look at how does our reconstruction compare to the high quality data reconstruction, and that defines our mean square error loss. With that mean square error loss, we can back propagate that mean square error loss and train or update that denoising block, that convolutional neural network that's inside that red box, in order to deliver a prior image that, when run through all of these modules, will deliver an image that corresponds to the high quality data case. Now, the other big benefit here, just to really emphasize it, is that we can put our MR as an input into that denoising network, and our network will learn how do we best exploit that MR information in order to deliver a PET image that best agrees with pure high quality PET only data with no MR involved. Okay, so that's a really good way to use MR. Okay, this is, I'm running out of time here, but that's a bit more detail into a network I published with my former postdoc. This just published last year, IEEE TRPMS, where indeed we've got the MR information going into there. We've got the PET going into this denoising network. It's going also into the EM update. We're fusing them together, going for a whole series of blocks to give our reconstructed image at the end there. And the formula, which I won't go into in detail, again, is just that map-EM method that we've seen before. We've got the EM update, and then we've got the EM update with our denoised update, where our denoised update has been learned by this deep learning methodology, where we've just back propagated the discrepancy between our image and the high quality reference that we want it to be. So it just learns how to best use the MR, how to best do the denoising, such that the end point looks like it came from higher quality data. So a very powerful concept. Okay, what are the kind of results that we get? So those are shown here very quickly. There's our noisy OSCM. This is for using 100 times fewer counts than our high quality reference, which is shown here. For simulated data, this is the MR data here, of course. That's conventional OSCM. Here's a conventional map-EM. And of course, with map-EM, that's going to use MR, but it could be using it wrongly. It's just using it in our, we've been using the similarity maps. We're making claims about how it should look. We could be wrong. The benefit with deep learning, which is shown on the far right-hand side here, is that it's learning how to make use of that MR information without our presuppositions about similarity maps and so on. With real data from the MMR, we've got a high quality reference shown here for 30 minutes of data. This is now OSCM with just 2 minutes of data, and obviously it's got a performance loss here. Deep learning shown on the right hand side here. I hope you'll agree it's done a much better job than conventional OSCM. and it's getting pretty close to the high quality reference. Obviously here, this is test data that would not used in the training of that deep network in every single iterative update. Okay, so this is the very last thing I want to say in the closing few minutes now, that we can do the same thing, and this is work I've been supervising by Guillaume Corder, who I think is on the call here. What we've done is what I've just been explaining there for the PET process. So I just refer you to all that I've previously described to understand that top row there. But also you can do the same for the MR, and MR reconstruction has been benefiting from deep learning for quite some time now to deal with undersampling. There's Hamernick's work that has done that, where you just learn what's the best regularized prior for MR reconstruction. But what we do with the synergistic is to now, a bit like what we saw with the conventional synergistic reconstruction, we just now interconnect every possible update. So that means that a given update of the PET reconstruction not only can take on all the previous MR iterates, but can also take on board all its own previous iterates. So we get the self-guidance, we get the guidance from the MR, and all of that information at any given iteration is learned. Again, that's the key point. All we're doing is making suggestions to the network for each iterative update to say, well, at iteration 10, you might want to use iteration of 2 of the PET. You might want to use iteration 4 of the flare reconstruction. The deep network learns what it is that it needs to use to deliver the best possible image at any given update. So a very powerful concept. So we've put out a conference record last year. It should be coming out this year, but it was presented last year. And we're hoping to present again this new enhanced version of this synergistic network. We're hoping to present that later this year. Okay, so these are the early results from that. I think we've got far better results to come, but just to emphasize that it can deal with some of the conventional problems. And in fact, on this slide, it's a bit of an unfair comparison. We're just comparing OSEM with deep learned methods. And obviously you can see the deep learned methods are completely outperforming conventional OSEM. That's probably a very easy thing to surpass. But just to say that this synergistic network is doing slightly better in this region, because in this region there's an MR unique feature that isn't present in the ground truth PET, and our reconstruction here seems to do a fairly good job in that unique region, whereas a more naive method that's not synergistic begins to nonetheless pick up some of the MR information. Okay, so in summary, I think I've got us back on time now, which is good. We've got a whole suite of methods from very early days to the current day now, a whole suite of methods for exploiting MR information in PET reconstruction. But I really think that the best we can ever do is the kind of network I've just been showing you, where we unroll the reconstruction for MR, deep learn the best prior, unroll it for PET, deep learn the best prior, interconnect the two, give every single iteration every opportunity to exploit all the previous information up to that point in order to match the fully sampled data for MR or a high quality, high count data set for the case of PET. But nonetheless, as I said at the bottom here, really it's PET that's grabbing all the benefits here. But if you stay just in MR, if you're an MR only person, then these methods, I mean, it's just waiting to happen really. Just synergistic MR reconstruction with deep learning should be very easy to do. Okay, so that is my last slide, and I'm happy to take any questions.